we have f of x, y, z equals y times zi plus x times zj plus the quantity x times y plus 2zk. Notice the difference here. This is a 3-component function, 3 variables, right? X, y, and z. So we're gonna take a leap of faith here and assume that the potential function does exist, and we're gonna try and find it. Okay, so it would be maybe a little more difficult to guess at a potential function, or you might be able to do it, but let me show you a more formal way of doing it. So if we assume that lowercase f exists, then we know that this component with respect to lowercase f would be what? F sub x, little f with respect to x, the derivative of little f with respect to x. What about this component? F sub y. And this guy would be f sub z. So I'm going to use every bit of that information to recover f. So here's what I can say then. F of x, y, z, remember, and I don't always write down the letters that stand for the inputs, but on this first example, I want to emphasize, yeah, it has 3 inputs, right? X, y, and z. Should be, well, couldn't we integrate this first component with respect to x, since it's f sub x? So it's the derivative of y times z should be the derivative of little f with respect to x. If I integrate it, it's like a partial integral. If I integrate it with respect to the variable x, I should at least be able to partially recover the function lowercase f. Now, why won't I be able to stop there? You'll see. Okay, so if we integrate this guy with respect to x, what exactly do we get? Let me work to the right a little bit. X times y times z, if we go in alphabetical order, plus what? Okay, but what is a constant with respect to x here? What? Yeah, y and z's we're considering when we take it's kind of like when we take a partial derivative. If we have a function f of x, y, for instance, we take a derivative with respect to x, we consider y constant, right? It's a function of y and z is your constant. Yeah. So we'll call it g, and we'll add in this guy. This guy is this guy is your constant. Remember, you always, when you take an antiderivative, you add in a constant. Now, if you go backwards and take the derivative with respect to x, the g of yz will go away because it doesn't have anything with x in it. So that's why we have to consider it. Is it necessarily there? Could it be 0? Yes. But we don't know, so we have to consider it. Does that make sense? Okay. So that's a representation of our scalar function, but we need to find out what g of yz is. See if it's a true constant or if it's a function of either y or z or both. Well, I haven't used the other 2 partials yet, right? From f, the vector field. So let's go ahead and take the derivative of this thing we just found. So let's take the derivative of this guy that we just found with respect to y now and set it equal to this guy. That's my plan. Does that make sense? Okay. So let's, and now I'm going to leave off the extra notation. Let's take the derivative of the guy I just found with respect to y. What does that leave me with? For this first term? X times z. Did you say z? All right. Canadian in here. Oh, and then, whoops, I didn't mean to say equal. I meant to say plus what? Yeah, we'll use g sub y of, and I'll need the notation here, yz. So take the derivative of this guy with respect to y, okay? Then we're going to set it equal to the j component in the vector field, x times z. So make sure you're focusing on the right thing. Now, this equation. Yeah, if you subtract x times z from both sides, then from this result, and again, you guys can work down in your paper. I'm working across because my screen is wider across than it is down. So what do we get? We get that if you subtract x times z from both sides, we get that the partial of g with respect to y of yz is equal to 0. So what does that tell us exactly about g? Not g sub y, g. You have to think of the worst case scenario. It's only a function of z. It could be a constant, right? But it could be a function of z, yeah.
Where'd you get the g sub y?
I took the derivative of the guy that I encircled in orange here
Oh, okay.
with respect to y, so I could set it equal to that guy because I know that's f sub y. Does that make sense? Okay, so my conclusion is this. So g sub y of yz, actually, let me go back up to the original function. So g of yz then could be just a single function of z. It could be a constant too. I don't know, but we have to put in the worst case scenario. Does that make sense? Because when you take the derivative of a function of z with respect to y, you get 0. That's the logic here. So if you take the derivative of h, this thing I'm calling h down here, switching notation on you, with respect to y, if this is just a function of z, then yeah, that's 0. Does that make sense to you? Okay. So now here's what I have. I have then that f of x, y, z has to be x times, can you see my cursor? X times y times z plus g of yz, which is h of z. I know, it's weird the first time you see this. I still remember the first time I saw this. I'm like, what? What is he doing? Now we're almost there, right? What haven't we done yet? What haven't we used yet from our vector field? F sub z. Okay, so we're going to use it right now. So what do I have to do to make use of this third component of my vector field? What do I have to do with my potential function as it is? Take the derivative with respect to z, right? And then you can set it equal to this. So f sub z, leaving off the function notation, would be what? So x times y plus, we can use just prime notation now, right? It's a single derivative. H prime of z. Sorry, I switched notation on you, sorry. But it's actually helpful because the more times you see the different notation, the more you'll get used to it. So I'm switching between prime notation and subscript notation and all that. So we set that equal to the third component, x times y plus 2z. And we're almost there. So what does this tell us? What does this equation tell us? Okay, so h prime of z is equal to 2z. And if you want to formally take the derivative, or integral rather, of both sides of that, you can recover h of z, right? But I think you can do that in your head. So if that's true, what does h of z equal? Well, technically z squared plus a constant, but it just says come up with a potential function. So in our answer, we'll leave off that plus c. But that is a true constant now, isn't it? So my potential function, hold on just a second. So my potential function then, use this guy as a guide, is f of x, y, z equals, you guys tell me, x, y, z plus z squared. And again, we could put in the plus c, but we don't have to. Because usually when we get a potential function, we just use it to evaluate an integral using the fundamental theorem of line integrals, and the c would cancel out if you use that theorem anyway.